So this is a experiment you can try yourself. If you're on a highway, you could just pull over to the side of the road. If you go over a bridge, just keep this in mind. You can grab a rock or any sort of dense projectile and drop it off the side of the bridge. And it's easier if there's a river below because you could see it kind of enter the water and hear it a little better when it hits the ground or hits the water below. And you could determine how tall the bridge is by just counting, 1 Mississippi, 2 Mississippi, 3 Mississippi, in order to time how long it takes to fall, okay? So let's read our problem. I'm sorry for my handwriting, but I'll read it to you, and if you can copy it down. A rock is dropped off of a bridge to determine the height of the bridge. It falls for 2.5 seconds before it hits the river below, okay? And here's our diagram. You can see that the rock starts moving slowly with small spacing. The spacing gets larger and larger until it hits the water below and makes a kersplash sound. And what I want you to do is calculate the height of the bridge. That's the first thing we want to look at, okay? So we could look at our equations that you just copied down, and we want to calculate height right here. How tall is that distance? Ooh. I call it a distance. I kind of gave it away. Well, height is not a velocity and it's not a time, but height is a distance or length, right? So we're going to try and calculate d, and that's going to give us the height of the bridge, okay? So that's our equation. We're going to use g equals a half gt squared. We're going to assume we're on Earth, so g is going to be 9.8. Remember from our chart, Earth has 9.8 for g, okay? And we're going to calculate distance. D equals a half 9.8 t squared. What are we going to plug in for t? The t is the only thing that's squared, so it's 2.5 seconds. Now on your calculator, multiply a half times 9.8 times 2.5. I'm going to do it over here. Oh, the 2.5 should be squared as well. And I got a height of the bridge. Remember, the unit for 9.8 is meters per second squared, so our distance is going to be in meters. And that's what I got on my calculator, about a little over 30 meters tall, okay? So basically, that's kind of tall, too tall, that's like a football field tall. All right, guys, so that's A, how to calculate the height, which is the distance. Now I want to do a letter B too, okay? So letter B is calculate, copy this down, the velocity, so how fast is the rock moving right before it strikes the water. At the moment before it hits the water, it is moving the fastest it could possibly go right before it hits the water, because it keeps falling and speeding up until it hits the water, and that's when it slows down, after it hits the water. Okay, so the velocity right before it hits the water is the final velocity. Some people make the mistake that the VF in this equation, they think what I mean by that is the velocity after it hits the water. What I mean, when the final velocity is the velocity at the end of falling. So right before it hits the ground or right before it hits the water, that's what the final velocity is. Right before hitting ground. In this case, right before hitting water. Okay, that's what the final velocity is. It's not zero. I know it stops eventually at the bottom of the river, but that's not the final velocity. The final velocity is right before it hits the water, at the end of falling. Anyway, g is going to be 9.8 because we're on Earth again, and the time is still what we used for letter A. It's the same problem. We're going to use the 2.5 seconds for time here, okay? So, pretty simple math here. 9.8 times 2.5 gets us the velocity right before it hits the water. 24.5 meters per second is our unit for velocity. Same unit we used in kinematics for velocity. Now remember, we said after 1 second of falling, the rock will be going about 10 meters per second, because that number is close to 10. After 2 seconds of falling, it'll be going about 20 meters per second. So it kind of makes sense that after 2.5 seconds, it's going about 25 meters a second. If it was falling for 3 seconds, it would get faster, but in this case, it's not, you know. Okay, guys, so there's your examples of how to calculate the height of something when you drop it, and how to calculate the velocity right before it hits the ground, okay?